This video series is about randomization tests, and so far we have looked at randomization tests using signs and randomization tests using original scores. By original scores, I mean the scores that we obtain when we measure the participants in our study. In this video, we are going to learn about the Wilcoxon signed rank test. In this test, we replace original scores with the ranks of the scores. So let me begin by talking about replacement scores. That is, when we decide not to use the original measures, but to replace them with something else. There are many types of replacement scores that we could use, but in this video series, I'm focusing on three of them: signs, ranks, and normal scores. And then, of course, we could leave the original scores intact, giving us a fourth method. Now, why would we change original scores with replacement scores? There are a variety of reasons that we may wish to do this. One or more of the following reasons might indicate it's a good idea to use replacement scores. If we want to change the hypothesis from what it is if we use original scores, we should use a statistical hypothesis that matches our research hypothesis. And maybe the research hypothesis is not closely aligned with the hypothesis that we will use if we have original scores. A second reason is to address the level of measurement. Original scores requires you to have a certain level of measurement. Maybe you don't have that, or maybe you can obtain more reliable data if you use a different level of measurement. Another reason to use replacement scores is to reduce the conditions for valid inference. As long as we have met the conditions for valid inference for a particular type of score, there's no problem. But what if we haven't? Or what if we're not sure about it? We may wish to reduce those conditions in order to increase the accuracy of our probability estimates and thus the validity of our study. In nonparametric statistics, when you have larger sample sizes, for some types of scores, you can take on quite a computational burden. So we might use replacement scores in order to ease that computational burden. Finally, it may be the case that by replacing the original scores with some replacement score, that we can obtain more power. That all depends upon the underlying nature of our distribution. And if we know something about that distribution, we may be able to choose a more powerful test than the one that we would obtain if we use the original scores. At this point, this is a fairly abstract list, so let me give you some more concrete examples. If you have reached this point in these video series, you will have watched my series on the sign test. If you have not, you should do so, because I'm going to compare analysis with original scores to analysis with the sign test. Now, indeed, for any of these replacement scores, one or more of these reasons may be valid for using such scores, but given that at this point we've primarily focused on using signs and original scores, I'm going to go down the path of that comparison, keeping in mind, however, that in the future, you are going to see these reasons appear again and again as we consider different types of replacement scores and different types of distributions. Let's start with the change of hypothesis as a motivation for using replacement scores. In the randomization test with original scores, the hypothesis is that the median difference equals 0. That is, we are focusing on the center of the distribution, with the median being used as the definition of that center. If you replace the original scores with the signs of those scores, you have two options. You can continue to focus on the median of the different scores, that is, you can continue to focus on the location of the distribution and how much that location shifts as the result of a treatment, or you can focus on the proportion of the matched pairs in which you obtain a plus sign, that is, in which the member of the pair that is in the treatment condition outperformed the member of the pair that is in the control condition. This would be more closely associated with a research hypothesis that states that the treatment will help some proportion of the population improve, in essence switching the focus from a hypothesis about distribution center to a hypothesis about proportional improvement. Sometimes we use replacement scores to address the level of measurement. When we use a null hypothesis that the median of different scores is equal to 0, we are assuming a continuous underlying construct and measurement of participants along that construct using a quantitative measure, that is, either interval or ratio. On the other hand, if we focus on the proportion of the distribution that is helped by the treatment, We can use dichotomous categories. We don't even need numerical data. We can simply compare the members of each pair and determine whether the treatment participant or the control participant improved. We could use ordered categories, that is, rank order, in order to determine which member of the pair was more successful. Or we can still use interval or ratio measurement. It's just that we will dispense with the quantities in favor of the individual signs. We can use replacement scores to reduce the conditions for valid inference. Again, when we're using the null hypothesis that the median difference is equal to 0, we have two conditions that we could potentially change. We are using a quantitative measurement, and we randomize within pairs. If instead we're looking at a null hypothesis about proportional success, we can use any level of measurement, and no randomization is required. You could have two members of a matched pair that you were unable to assign to one condition or the other. That can happen for a variety of reasons. For example, if we were comparing smokers to non-smokers, we cannot randomly assign to smoking condition. So if you do not have randomization, you have not met one of the conditions for valid inference for a null hypothesis about the median of difference scores, but you can look at proportion success. And then we might use replacement scores in order to ease the computational burden when we do the analysis. If you're new to nonparametric statistics, the idea of a computational burden might be new to you. Yes, you may be used to computational complexities in the parametric world, but that's different than the burden that we have in the nonparametric world, which is not a complexity issue, but a computation issue. Take a randomization test with original scores. We know that we calculate the critical value or the p-value based upon the various sequences of plus and minus signs associated with those original scores. We know that the number of sequences of those signs is 2 to the n, where n is the number of observations. So in an example that I have been using throughout this video series, where we had 6 observations, we had 2 to the 6th, or 64 different sequences. That made it easy for me to teach this to you because we did not have a high computational burden. But imagine if we had 10 observations, that is 20 participants matched into 10 pairs, and we obtain 10 different scores. Now we have 2 to the 10th, or 1,024 sequences. That is still fairly manageable. Yes, our probability distribution table is going to get fairly large, but we can handle this. But let's up the ante a little more. How about 30 observations, 30 different scores? Now we are dealing with 1,073,741,824 different sequences. I don't want to think about how much scrolling that I would have to do on my screen in order to get through that probability distribution table. Even dealing with just one end of the table, where I may be looking for 5% of the values to put in the critical region, 5% of this number will still leave me with a fairly hefty duty. And let's do one more. What if we have 200 participants matched into 100 pairs so that we have 100 different scores? Then the number of sequences is 2 to the 100th, and don't ask me to attempt to read to you that number. I am not going to do it. You see now why there is a heavy computational burden. In fact, if we want to calculate the test statistic for all the possible sequences with original scores, and there are this many sequences that we need to not only figure out, but then calculate the sum of the positive scores as our test statistic and store those and keep track of whether there's any duplicates, it's easy to realize that unless you have access to one of the world's most powerful supercomputers, this is going to be outside of our reach. Now consider a randomization test with signs. If I had 100 matched pairs, would I still have this many possible sequences? Indeed, I would. But since I'm focusing only on the signs, I can use the binomial formula. That is, it doesn't matter how big n is and how big x is here. I can do the calculations and do it fairly quickly. If I'm using a software package that has a binomial test function, it's not going to worry about how many observations I have in order to provide me critical values or p-values or whatever it is I need. And then finally, we use replacement scores in order to increase power. If we conduct a randomization test with original scores, that is uniformly the most powerful thing we can do when the population distribution is a normal distribution. Remember from a previous video that a randomization test with original scores and the t-test converge in terms of their probability calculations. Both of those are UMP, that is uniformly most powerful, if we know that we have a normal distribution. So we would choose original scores as our quote-unquote replacement scores, meaning we're not going to replace it with anything, or we're going to replace every score with itself if we know we have a normal distribution. By contrast, a randomization test with signs can be more powerful when the tails of the distribution are heavier than the normal distribution. That is, we have more outliers or more individuals at the extreme than we would expect with the normal distribution. So knowledge or anticipation of the underlying distribution, either on theoretical grounds or from past research, can help us choose replacement scores that will give us high power. And so now back to the Wilcoxon signed ranks test. We're finally there. But we're going to start with a randomization test setup that you have seen already. This is the beauty of randomization tests. The setup is the same regardless of whether we're using original scores or if we're using replacement scores. When I set up the randomization test for signs and then set up the randomization test for original scores, I did the same thing, and I'm going to do the same thing again now. We're going to match participants into pairs based on extraneous variables. The pairs must be independent of each other. The members of each pair are then randomly assigned to conditions, and the measurement scale is at least interval, that is quantitative data, as we measure each participant on a continuous underlying construct. The null hypothesis is about the center of the distribution, with center defined by the median of the different scores, and that center is viewed as 0. Although we know if we're hypothesizing a different median besides 0, we can always adjust to 0, simply subtracting that hypothesized value from every score. And recall that if this null hypothesis is true, and if we swap the control and treatment participant within a pair, the absolute value of the difference will remain the same, but the sign will switch. Even though the setup of every randomization test is the same, what makes one test different from another is the test statistic. And for the Wilcoxon signed rank test, the test statistic is this. Let T be the sum of R sub I plus, where R sub I plus is the rank of the absolute value of the scores. That is, we ignore the sign when we rank. And if our original score is greater than 0, where R sub I plus is the rank of the score without the sign attached, if that score is greater than 0, that is, if it is positive, and R sub I plus is 0, if it is negative or equal to 0. In practical terms, what this means is that we rank the absolute value of the original scores. We add up the ranks that are associated with the positive original scores. Here are some scores that I have used in a previous example. These are the original scores. Let's go through the process. First of all, we want to rank these scores ignoring whether they have a plus or minus sign. So when I rank these, the score of -1, ignoring the negative makes it a 1, has a rank of 1. The next highest score is 2. Again, I'm ignoring the negative. The next highest score is 3, so it has a rank of 3. Next is 6 with a rank of 4, 7 with a rank of 5, and finally the highest score, 12, has a rank of 6. I now will add up the ranks that are associated with positive original scores. So I'm going to add up the 3, the 5, the 4, and the 6 to give me a test statistic of 18. An exact test is to place the values of this test statistic most incompatible with the null hypothesis in the rejection region. In the case where we're looking at a treatment against a control and high values on our measure indicate a positive outcome, then high values of t are going to be most incompatible with the null, and they will be the first into the rejection region. Then, of course, we build that rejection region so that if the null hypothesis is true, the probability of us observing a t that is in the rejection region is less than or equal to our tolerance for error, alpha. That is, we're going to maintain our type 1 error rate at less than or equal to alpha. So here is a picture you are familiar with. All the plus and minus sequences are the same as what you've seen in the past. What has changed is on that top row, we are now looking at ranks instead of pair numbers like we did with signs, or scores like we did with the original scores randomization test. Thus, when we have all plus signs, we're going to add up all the ranks and we get a value of 21. By the way, a little shortcut to tell you what the maximum value of t can be, that is what you'll get when you add up all of the ranks, is that maximum value of t is the number of observations times the number of observations plus 1, quantity divided by 2. So in this case, we had 6 observations, so we have 6 times 7 is 42, divided by 2, which is 21. You didn't really need to do that here, but imagine if you had lots and lots and lots of ranks, then this shortcut might come in handy. We observed a test statistic value of 18, so our p-value is 18 and higher. That is, 1, 2, 3, 4, 5 different sequences will lead to a test statistic of 18 and higher. Therefore, our p-value is 5 over 64, the number of sequences, or 0.078. If our tolerance for type 1 errors had been set at 0.5, we would not reject the null hypothesis. If it had been set at 0.10, 10%, we would reject the null hypothesis, but that decision about tolerance for errors must always come before we collect the data and conduct the analysis.